Right now, we're going to start a new subject in some sense. It's going to feel completely brand new. We've been doing a bunch of counting, and we can count things about graph theory, but we're going to be studying graph theory now mostly for the remainder of the course. This is a broad subject in combinatorics, but doesn't just sit in combinatorics. It touches other subjects, geometry, topology, and a lot of things like that. All right, so we're going to start from sort of the beginning. We're going to take what's sort of the naive approach. So we're going to assume that certain things are just understood. Certain basic mathematical structures are understood, right? And I don't think you'll have arguments about this, but if you're a foundationalist, then you would probably want to clean some of this up and go into the foundations to make sure it all makes sense. All right, but we're going to start with a fairly normal approach. All right, so what is a graph? We're going to start there. A graph is a structure composed of something called edges and vertices. So that each end of an edge is connected to a vertex. Okay, let me highlight two words in here that we're going to have to define, sort of. Okay, got it. All right. Edges and vertices here. Okay, so let me explain what these are. And this is what I mean by taking sort of what's called the naive approach. This isn't meant to be like a low-level approach. It means we're going to have some understanding of what vertices are. So a vertex, and the plural vertex is vertices, is a point. Okay, so we have to accept that we understand what a point is, right? So like if you do a point in two-dimensional space, it'd have two coordinates. You could have a point on a number line. You could have a point sitting in three-dimensional space, right? So you have to have some notion of what a point is. And then an edge, which may be a little less clear, is structurally equivalent to what you call a line segment. Okay, if you want a mathematical structure that describes a line segment, it's fairly common to take, say, like the closed interval 0 to 1. Okay, so like take a piece of a number line, 0 and 1, and I've drawn this in such a way that I have emphasized that 0 and 1 are vertices. Okay, so I could have drawn it this way, as just a pure edge with no attachment to vertices, like that. Okay, so with this emphasis, I'm emphasizing that 0 and 1 are specified points. And this first thing is a graph. This second thing is not. This is an edge that does not have its ends attached to a vertex. Okay, so maybe I can note that. Right, this is a graph. A very simple example of a graph. This is not a graph. Okay, let's do some other examples and non-examples of graphs. All right, and that's really what I'm going to fill out this board with. So let's do one that's not overly simplistic. We'll actually bring it up again. So it has 4 vertices. Just like this. Okay, and I'm going to label the vertices. It's not super important what the labels are here, but I'm going to use capital letters A, B, C, and D. Now I'm common to also use lowercase letters or even numbers. Okay, so vertex labels can be whatever's convenient based on the context. If they represent people, maybe the names go here. Or if they're cities, or if there's some other object that a word makes sense, you can use words as labels for the vertices. Now these edges in this particular graph are in an unlabeled form. You could label them, so maybe for fun, I'll label them with numbers. and then that if they are labeled, or if the graph is not labeled and you label them, that gives you an easy way to talk about the edges if you need. Sometimes you can just use the vertices that they connect as labels, but this graph you cannot. So I'm going to introduce some vocabulary words as we kind of go through a few examples here. This is referred to as a multigraph. It's also a graph, but it's, if you want to be a little more specific, it's a multigraph. The reason why it has that name is it has these multi-edges. So let's give a reason why. There is a multi-edge connecting A and D. And that's true of C and D as well. Okay. That's when there's multiple edges connecting there. And so you can kind of refer to this structure as a multi-edge. Also, you can refer to them as individual edges, right? Edge 1 and edge 2. But there's more than one edge connecting A and D together. All right. What are some other examples? So you could do this. I like to bring up this example. It's a fairly interesting one. It's very tiny. It's one vertex A. And the edge actually connects both ends to the same vertex. And there's actually nothing in this definition that says you can't do that. So each end of an edge is connected to a vertex. Well, each end is connected to a vertex. In this case, the same vertex. I'm not going to go through the process of labeling this edge, because I don't think it needs a label. But this is something that's referred to as a loop for short. Okay. However, at this point with this much as examples, I think it's important to introduce the word adjacent. Okay, so pulling from both of these. In the second example, A is what you call self-adjacent. All right, there are no self-adjacencies in the top example, but you could say A and D are adjacent to one another doubly. They're doubly adjacent to one another. Okay. A and B are adjacent. Okay, so what does this mean? This means that they are connected by an edge. More or less, you could take connected by an edge and copy and paste the word adjacent. So A and B are connected by an edge, so A and B are adjacent. A is connected by an edge to A, so A is adjacent to A. Right? Although other word choices could be used there. Okay. So that's how you would use the word adjacent. It means they are connected by an edge. All right, let's look at a few other examples here. Could have an example that looks like this. I'm not going to label these vertices. The whole point of this example is you should notice these are actually in two pieces. So this graph is disconnected. Right? Let me put this in quotes because connectivity, I think, takes a little while to build up to, but it's very easily understood as a concept. Okay, so we'll eventually, when we get to doing searches, we'll be able to really nail down what it means for a graph to be connected. We'll define it a little sooner than that, just because we'll need it. But as of now, just go ahead and take for granted. This is a disconnected graph. There are actually two pieces. There's no way to get from one vertex to some of these other vertices, and that's how you tell if it's disconnected. Okay. Some other terminology that might be helpful is this interior triangle is what you call one of the connected components, and then this exterior triangle is another connected component. Let's see, how about another example here? All right, this one has what you'd call an edge crossing. All right, typically not a big deal. in many applications, we're going to allow edge crossings, but we're going to actually spend a chunk of time where we're going to discuss whether or not we can avoid having edge crossings. This is due to a few important applications that are physical applications often, but think of it this way. So a graph is really just a structure made out of points and line segments. And then you have to put this graph somewhere. And right now what I'm doing is I'm working on a light board, which is a flat two-dimensional surface. This is the same for paper, or a chalkboard, or a whiteboard. These are all two-dimensional surfaces where I can place the graphs. You could think about putting them in three-dimensional space. In fact, I have some examples, just not with me for now, but like if you think about having, say wire as the edges and maybe little BBs or something as just a model, you could make these things in 3 dimensions. And then the notion of edge crossing would be fairly like pathological, right? The idea of making edges pass through each other in 3-dimensional would be actually fairly difficult to achieve, but this happens a lot when we have to draw these graphs on a 2-dimensional surface. This is sometimes just a defect of the fact that we're stuck in 2D drawing these things. However, there are specific applications where you don't want an edge crossing, right? And so if you are into some computer engineering aspects or some sort of logistical planning things, crossing lines is not always acceptable. So if you are on a chip and trying to connect together transistors or CPUs or whatever, there are certain restrictions about how many connections you can make before you end up with some problems. Same thing with utility lines. So it's quite common to have to go under another utility line, or if you're making a subway system or whatever you're making, you can't just connect everything and expect to be able to do routes that don't cross or go under. So this is an important thing, but keep in mind, this is okay here, we just have an edge crossing. This is not a vertex, by the way. Just because there's an edge crossing doesn't implicitly mean there's a vertex there. So keep that in mind. It would require some good practice of, you would need to put a dot there to emphasize, unless it's understood that there's not a vertex there. Okay, let's see. Yeah, let's do the next examples on a clean board. So I'm going to see you on the next video.